Yeah, so I'm pretty excited today. We've done the partition function for a two-level system last time, and that's, like I said, it's a classic system. It's pretty simple, just two levels. And so today we're actually going to start talking about real molecules, so I'm super excited. We're going to do translational partition function today. Next time, rotational motion, and then vibrational motion and electronic motion. But today we're really going to be focusing on how we think about gas phase molecules, because that's our translational model. And so we're going to pull forward what we did in the fall with the particle in a box, and we're going to use that information today. So I think it's pretty exciting. That's why I teach this stuff, right? So, all right. So the partition function, again, is that denominator in the Boltzmann distribution. It's called the partition function. It's how we partition the molecules and their various energy levels. And it's this total energy distribution summed over all available states. And so it's kind of a measure of how many states can be populated at that temperature. So for a two-level system, the minimum was 1. If we cool it way down, it's all in the ground state. So our partition function was 1. Since there's only 2 levels in a two-level system, even at infinite temperature, the maximum for that partition function would be 2. And because you only have 2 levels. But now we're getting into translational motion. And if you think of our particle in a box, that L was in the denominator. So if the box got smaller and smaller and smaller, the spacing of the energy levels got bigger and bigger and bigger. And so then you would see quantum effects in a really tiny box. But what about in a room this size, right? We've got, maybe 4 or 5 meters wide is our box in this dimension. And so those energy levels have really pushed down to being almost touching, right? There's nothing physical that can't touch, but if you were to draw them, your little lines would be touching each other. There'd just be a continuum of energy levels. So, and again, we use that temperature. That temperature becomes the measure of the total energy available in that partition function. Let's think about the two-level system and look at our probabilities. So I said, at low temperature, the partition function goes to 1. So this blue, the blue curve is the partition function. And then we do see quantum effects in a two-level system, obviously. These are probabilities here. So the ground state is red, the excited state is green. And so at really low temperatures, what's the probability of being in the ground state? It's 1. And what's the probability of being in the excited state? It's 0. Now, the way this temperature is plotted, it's the temperature of the system divided by 298 Kelvin. Okay, so if we raise the temperature and we get to 298 Kelvin, so here's the temperature of the system divided by 298 Kelvin, and so here we are in this two-level system where the spacing is 400 wave numbers. And remember that at room temperature we have about 200 wave numbers of energy. Okay, so we have about half the energy we would expect to excite that molecule to 400 wave numbers. At room temperature, we have 200 wave numbers of energy. The first excited state is at 400 wave numbers of energy. And yet, look at this, there's a non-zero probability of being in an excited state. Even though we only have 200 wave numbers of energy, some of those molecules are in an excited state. And in fact, they have to be, otherwise we wouldn't have any energy in the system. If the ground state is 0 energy, for the system to have any energy in it, some of those molecules have to be in the excited state. And how they get there, that's where the quantum question comes in. How do all of those few molecules collect all the energy and end up in the excited state? Okay, it's through photons of light, essentially. But as far as how that happens, we still don't know how this jumping occurs. Remember, Schrodinger said, if we don't get rid of all this quantum jumping, he called it this damn jumping, I would be sorry I ever got involved in this. Well, Schrodinger, we never got rid of it. Mm-hmm. We don't know how the molecules hop up and down. We can make it happen with photons, but we don't know what causes this particular particle to absorb a photon. All we know is the average effects. And so in this part of the course, we're just looking at the average energy of the system. Some of those molecules, it looks like it's about 15%, it's a little more than 10%, but not quite 20%, are in a state with 400 wave numbers of energy. The rest are at 0 energy. And you average all of those and you get 200 wave numbers of energy. When we get up to 400, now we're sort of twice the the room temperature. So we have, 4 to 600 wave numbers of energy. We see there's quite a bit more probability of being in the excited state, and less probability of being in the ground state. Notice the partition function has gone up. When you cool it down to absolute zero, you're all in one energy level, the ground state. But then as you heat it up, you see now it's sort of asymptotically approaching 2, which would be equal partition, half in the ground state, half in the excited state. Okay. And so this probabilities approach the 50-50 mark at the higher temperatures as expected, and that partition function approaches sort of a count of the total number of energy levels. So now let's look at the translational partition function. So we're going to use, for translational motion, a particle in a box, only we're going to be dealing with a pretty large box, like a room-sized box. We could just even think of like a 1 cubic meter, because then the units will all work out really nicely. Okay. And so the energies are substituted into this definition of the partition function. So what could we use for this energy? We know there's an energy equation that is a function of the quantum number, okay? And that's that particle in a box energy equation. So we just go dig out our PChem 1 notes and find that energy equation and stick that in for epsilon. And so we're supposed to sum over all of those. N equals 1 to infinity. We're just going to start at the first quantum number and count to infinity. So Excel can go up to 67 million cells or something like that. So we can't even go to infinity in Excel. So how would we do this sum from 1 to infinity? yeah. But if we get away from numerics, there are other tools that we have in calculus that we could use instead of doing a discrete sum. No. Yeah, integration. So we would just say, okay, if we're going to sum to infinity, how important is each individual quantum state? It's essentially infinitesimal. And so we could turn this into an integral and integrate with respect to n. So instead of summing over n, we're going to integrate with respect to n, because each individual quantum state and how it in this range from n equals 1 to infinity, the differences between these quantum states is going to be really small. And so it is that limit as delta n goes to infinitesimal, we could make this an integral. So we can integrate this equation with respect to n. And so then we get this result. So all of those things come out as the inverse, and so they end up sort of looking upside down. And then we have this, it was all to the 1/2 power, so we had L squared to the 1/2 power, so L just comes out by itself. So I just have this coefficient times L, so the length of the box. And so this is in 1 dimension. Also, let me point this out too. This, a lot of times T stands for temperature, but in this case, this means translation. Okay, just to be clear. So this is the partition function, the translational partition function. Okay, and this is in 1 dimension. Okay, we'll make it go to 3 dimensions in a minute. Now, I didn't recognize this, and I'm pretty sure you didn't recognize this, but they say that this term, h squared over 2 pi mkt, has the units of length, okay? And so they call that the thermal wavelength. And so they call this a new useful term, the thermal wavelength, and that it looks like the de Broglie wavelength. Now, how does it look like that? Well, this h squared to the 1/2, that's sort of h over this other stuff that would have the units of momentum. And so it's sort of, somebody says, looks like the de Broglie wavelength or the de Broglie wavelength. And so we call that the thermal wavelength. It's a function of temperature. Okay, so if we raise the temperature, the thermal wavelength gets smaller. Okay, if we lower the temperature, that thermal wavelength gets longer. And if the thermal wavelength gets long enough that it's on the same scale as the length of the box, then we would start to see quantum effects. But if that thermal wavelength gets really, really small, at higher temperatures, then we would not observe quantum effects. And so it's pretty unlikely. Well, I'd say it's almost impossible to see quantum effects in translation in regular sized volumes. Okay. And so since this lambda is this piece over here that's upside down, lambda is going to be on bottom. It looks like an A missing the bar. That's a capital lambda. Okay. So this is the de Broglie wavelength was a lowercase lambda. This is an uppercase lambda. Okay. And so this is the shorthand for the translational partition function in one dimension, is the length of the system, like the box it's in, divided by the thermal wavelength. Now that thermal wavelength is going to be really tiny, and so this is going to be a huge number for the translational partition function. Now if we were to take this in a room, like a real volume, not just a length, we have the x direction, the y direction, and the z direction. So we have a quantum number in the x direction, a quantum number in the y, and a quantum number in the z. And we could use the partition function, or the particle in a box, for all three of those. Just one is in x, one is in y, one is in z, but it would be the same integration. And so we would end up with a length of x, a length of y, and a length of z. And so there'd be this thermal wavelength cubed would be also in that. So let's look at it in 3 dimensions. So we have a particle in a room temperature, which is really hot, box that's, in 3 dimensions. So then we just extend this, and so we would have that thermal wavelength, the inverse of that thermal wavelength cubed. So it goes from a 1/2 dependence, we cube that, we end up with a 3/2 dependence. And we go from a single L length to a volume. So length, width, height, all multiplied by each other. And so that's where we end up with this volume. So that's a really funny equation. It's like a V and an upside down V. But that's a lambda actually. So that's our 3-dimensional partition function, is the volume of the system divided by this thermal wavelength cubed. And so then we can look at that. If volumes, that seems pretty specific to whatever system you have. Like this room has a certain volume, but what if we don't really want to measure the walls, right? Can we find a substitution for volume? Absolutely. The ideal gas law. So PV equals nRT, and so we could just swap that out and do nRT over P for the volume. And now it's just a function of temperature and pressure. We don't need to know the dimensions of the room. We just need to know the pressure. Okay, so that's pretty handy. So a lot of times, and that's this course, so get that trick in your head. If you ever need to get rid of volume, just use the ideal gas law and go with nRT over P. Then you don't have to worry about how many liters are we talking about here. We just need to know the temperature and the pressure and the number of moles. Now that is one thing though that complicates things. We were using N for the quantum number, and now N is number of moles. So you really have to pay attention to context, right? In looking at this system, you were like, well, we went from volume to the ideal gas law, nRT over P, so now this is the number of moles. And so let's take that lambda cubed and let's expand it all so that we can see what our temperature dependence is. Okay, we had in that lambda, it was temperature to the 3/2 power times another temperature. So we have 3/2 plus another 2/2, right? Temperature to the first power is temperature to the 2/2. And so 3/2 plus 2/2 is 5/2. This is crazy, but we have a weird dependence on temperature for our translational partition function. So it's temperature to the 5/2 power, or a 5/2 dependence. Okay. Probably at this point, the strangest dependence you've seen. You've seen things that are directly proportional and stuff like that, or inversely proportional. Well, this is a really weird one. Okay. And so this, for grins, partition functions are unitless. So let's prove to yourself that this mess is unitless. All right. So most of this course as well, doing problems, is all about the units. And so you've got to figure out what units to use. Like here's pressure. What unit would you use for pressure? Atmospheres is tempting, right? But would that cancel with anything else in this equation? We'll see. Okay, let's look. So let's see. Do we want to? Yeah, let's do the units first. Okay. So let's see if we can figure out what we've got here. Of course, what is our temperature unit always going to be in these calculations? Kelvin, absolutely. So we're going to have Kelvin here. Oh, what is this constant? Boltzmann's constant. Okay, what are the units for Boltzmann's constant? Joules, what? Joules per Kelvin. Okay, joules per Kelvin. So we have joules divided by Kelvin here. And so let's go ahead and break joules into its bits. Okay, so what is a joule? In terms of SI units, right? Okay, there's a meters squared per second squared, and there's a kilogram there. Now, how can you remember that? Do you just memorize that? Yeah, there you go. Put it on your note card. Exactly. Emily for the win. Okay. But do you remember just the basic, like F equals ma, right? Force equals mass times acceleration. Okay. So this is one of the ways I remember it, because this was ingrained in me so much, that force equals mass times acceleration. So mass is a kilogram and the acceleration is a meters per second squared. Okay, that makes sense. And then work, joule is energy, right? That's work. And so work is working against a force for a certain distance. Okay, so to get this from newtons, this is a newton here. A newton times a meter equals a joule. Okay, so that's where the meter squared comes from. So it's a kilogram meter squared per second squared. It's working against the newton, a force, for 1 meter gives you a joule. Okay. So anyway, that's where this kilogram meter squared per second squared, that's how I remember it. So that tells us we've got kilograms here. We're probably going to want our mass in kilograms too. Probably not going to use a mass directly off the periodic table in grams per mole. Okay. We got a mole over here, so maybe, but anyway, we'll do kilograms here. We've got a mole here. Okay. What for R? What are we going to use for R? Let's hold off on that one for a second. Let's look down here at Planck's constant. What are the units for Planck's constant? Pardon? Yeah, you got joule and second correct, but it's the per that is going to cause you problems. Yeah, exactly. Joules times seconds. Joules times seconds. Okay. Now, you may want to leave the joule if you're going to cancel joules or whatever, but you also may want to split it out. And this is the thing, you have to make these decisions when you're working with the problems. Sometimes you split one of the Planck's constants into kilograms, meters, and seconds, and other times you leave it as a joule. Just however the situation demands. It's up to you, okay? And so you could break this one out also as a kilogram, a meter squared per second squared. And so then the per second squared and that second will cancel the exponent, so that you could destroy that and get rid of the square, and so you have kilogram meters squared per second for Planck's constant. You got, it's cubed, so you got 3 of those sets of units to cancel out. And then pressure, golly, how many units of pressure can you think of? There's atmospheres, there's torr, right? Which is equal to millimeters of mercury, which is a really strange thing if you think about it. That's a pressure unit, millimeters of mercury. It's a length of liquid metal, right? But that's in a manometer, that's the pressure difference based on mercury. Sometimes, like if you're looking at the weather report, it's inches in mercury, which is totally strange. But yeah, inches of mercury, that's a pressure unit.
Pascal.
Yeah, there's a Pascal, right? And that's Yeah, what's the inches of water too? Yeah, exactly. And so Pascal, this is the one that's uses the SI units. Okay, so Pascal is a Newton per meter squared. So it's a force per square meter. And we've already determined what a Newton was up there. So that's a kilogram meter squared. Oh, meter, not meter squared. Per second squared divided by meter squared. So it is a hot mess of units. Okay. And then we have to decide on the gas constant. So there's two forms that you should have memorized for this course. Okay. There's joules per mole Kelvin. Okay. And then there's liters, atmospheres per mole Kelvin. Okay. So it's 8.3 or 0.082. Yeah, so you should have those two. I think those two gas constants we're going to use frequently enough that you should have them just committed to memory. And then depending upon what units are demanding in the rest of part of the problem, you can decide which gas constant to use. Okay, so that's, again, I'll leave it to you to show how this is unitless. Because some of these are to the 3/2 power, some are to the 5/2 power to Kelvin. You got a cube in the bottom with the Planck's constant and everything. So you think Sudoku's fun? This is even better. Okay. All right, let's take a top hat question. Okay. Okay, so here's our translational partition function, and I'm giving you a little multiple choice. This is to get you familiar with how we speak in text about equations. Okay, so that's the focus here. So which of those phrases would accurately capture the temperature dependence of the translational partition function? It's not meant to be tricky. And hopefully this will help you in the future be precise in how you describe equations. So that's another part, a goal of this question is to the precision of language. Hurry, hurry, hurry. Don't miss out. Okay. What's that? Yeah, that's right. I want to make sure everybody has a chance, but don't delay. Time's a wasted. One more? Okay, we're out of time. All right, so let's go. So here's our, yay, okay, good. Look at that spread, though. It's kind of funny. Yeah, a lot of people hedging their bets. Okay, so let's talk about these. Directly proportional means it's whatever, they're both on the top. They're both in the numerator, say. They're directly proportional, and it's to the first power. So directly proportional means to the first power. So it'd be temper to the first power in the numerator. If the temperature's in the denominator, that's what we mean by inversely proportional, but still to the first power. Okay, so directly or inversely proportional, all would be to the first power, and that's what you're assuming when you do your number over x equals this over that. How many people learn how to do those kinds of problems in high school, right? That was a big deal. It's like, okay, this changed, and I want to know how that changed. I'm just going to put that over x and this over this, and I'm going to see cross multiply and solve for x, right? Only works for directly proportional things. So that will not work for this temperature in this equation. You've got to take the power into consideration. So we're going to do a couple of problems related to that. Okay, because that's one of my favorite types of problems. What if you don't know the mass of the particle? Or what if it's a mixture like our atmosphere, nitrogen, oxygen, CO2, and so on, right? So you don't want to worry about the mass. You just want to know the temperature dependence. You don't need to know the mass if the mass didn't change. So you can cancel all of those things out, but you got to keep temperature to the 5/2 power. And so that's why this one has a 5/2 dependence on temperature. Now, when you say it has a 5/2 dependence, you may be thinking, well, does that mean there's 5/2 in front of the temperature, like it's multiplied by 5/2? No, that would be temperature to the first power, and that would be directly proportional. So this has to be an exponent. So when you say it has a 5/2 dependence on temperature, it has to be temperature to the 5/2. So it's a little nuance how we write about things. And so that's why I wanted to emphasize this. This has a 5/2 dependence on temperature. Quadratic would be temperature to the second power, and square root would be temperature to the half power. So there is a square root part of this. It's 5/2, but you can't leave out the temperature to the fifth. So it's temperature to the fifth. So if you're doing this on the calculator, temperature times, you know, and you got 5 there, temperature to the fifth, and then you take the square root, and you got it. So that's temperature to the 5/2. So that's how you do it. Some calculators have a little caret key, and so you could do temperature, the number, the caret, and then you could put 5 divided by 3 in parentheses and hit, you know, evaluate, and that would work as well. Okay, so that's the correct question. Okay, so we'll jump back to the PowerPoint. So let's do some practice problems. What's the thermal wavelength and the translational partition function for argon at 1 atmosphere and room temperature? Also, let me go ahead and label this. We'll talk about it later in the course, but this is SATP conditions. So you've heard of STP for gases, right? Standard temperature and pressure, but the standard temperature is 0 Celsius. Or 273 Kelvin. But what do we do for room temperature? That's standard ambient, so ambient. So this is standard ambient temp and pressure. Okay, so 1 atmosphere, 298 Kelvin, that's SATP. I want you to know that because I may use that in a problem. Like when I say blah, blah, blah at SATP, you're like, oh, heck, what's my temperature? What's my pressure at DW? But you should be able to like pull that out of your head and say, all right, or note card it. Yeah, and so let me move this out of the way here. So here's our mass. Let's go ahead and convert it to kilograms. And so we take that, we look up there on the periodic table, and we find argon, and we see that it's 39.95 grams per mole. So let's move the decimal 3 places and get it in kilograms per mole. And then divide by Avogadro's number, which gets rid of the per mole. And so we're left with the kilograms. So a tiny little mass, 10 to the minus 26 kilograms for argon, for a single argon atom. And so then the thermal wavelength is this equation here. So we have the mass and everything else is constants, and we know the temperature. So we can throw in all of this stuff into this big bear of an equation. I went ahead for Planck's constant and broke it out in kilograms and meters and seconds and so on. Now, let me just show you a trick to keep you from screwing up your calculations, okay? This is equal to 6.626. Look, if you're doing this in your calculator, divided by the square root of 2 pi 6.6. I don't know why I rounded one and not the other, but that's irrelevant. Okay. 3, 1.38, and 298. Do you see what I'm doing? I'm pulling all of those numbers out. Okay. Actually, let me erase this. I can type all those numbers in fairly reliably into my calculator and not make a mistake. And I get a number, and then that's multiplied by 10, okay, to the minus 34, okay. minus a minus 26 over 2. Where's that over 2 come from? Minus a minus 23 over 2. Yeah, see what I'm doing? I'm pulling all of the powers of 10 over here. And I can do a little order of magnitude analysis and get my power of 10. And that's maybe a simpler calculation so that you don't screw up the exponents in your calculator. I mean, yeah, or you may just be super reliable, okay? But this is a way to check your math. If you just can't find your mistake, you can do it this way, do it the other way, and you're like, okay, they both match. And maybe my mistake is somewhere else. Maybe I've got a units problem and I'm using the wrong constant or something like that. So this is another way to do it, but yeah. And so that's, it gets up 1.6 times 10 to the minus 11 meters. Now that's my thermal wavelength, okay? And if I'm in a reasonable volume, I mean, it could be milliliters, it could be the size of this room. Think about how small that thermal wavelength is. That's where quantum effects would emerge. If I got this room down to 10 to the minus 10 meters, like an angstrom, okay, then I would see quantum effects in translation. Make sense? So am I going to see quantum effects of translation in a normal volume, something I can see with my eyes? No, not at all, because this is the thermal wavelength, and any measurable volume size is going to be much larger than that, and so I'm just not going to see quantum effects from translation. That's sort of one of the take-home lessons today. We're just not going to run into quantum effects of translation. Are they there? Yeah, because the statistics match what we measure in real life. So this counting of energy levels matches what we see in gas behaviors. So we, I guess, believe in them, but we don't see them, right? This is kind of almost a faith statement, when we see that it matches the data, but we're not really able to detect it, And so then our volume, I just did a meter cubed, actually I did it at 1 atmosphere and room temperature. What's the volume of a mole? And so it's 24.5 liters, convert that to cubic meters. And so here we end up with our volume in cubic meters and our thermal wavelength cubed, which is in cubic meters. And we end up with this unitless quantity, which again is a kind of a count of the number of energy levels that are accessible at this temperature.
Where'd you get that volume again?
I took the SATP conditions and I just said 1 mole. Okay, so I took 1 mole of an ideal gas at 1 atmosphere and 298 Kelvin, and that's where I got that volume. Yeah, I could have used the pressure version of this equation, but I wanted to just come up with a volume, and so I thought, let's take a mole of argon and use that. Okay, so that's a lot of energy levels. 10 to the 30 energy levels are populated at room temperature. So once again, we're not really going to see quantum effects if we have that many levels populated. So let's see, does this make sense? Let's think about our particle in a box energy equation. What's the energy spacing for the particle in a 1D box in wave numbers? Remember, we know at room temperature we have 200 wave numbers of energy. So we have 200 wave numbers, that's our thermal bath. How far apart is the n equals 1 to n equals 2 wavelength or energy levels, right? How much the spacing in wave numbers between like the n equals 1 and n equals 2? We could do that. We could take n equals 1 in that equation and n equals 2 and take the difference. And so the difference would be this equation here. If I have a difference in energy in joules, if I divide that by hc, then it converts it over to wave numbers, if c is in centimeters per second. So I've done this little bit of algebra for you. I took E2 minus E1, and that's where that 3 came from, h over ml squared. It used to be h squared, but when I divided by h here, I got rid of one of the h's, and then c is in the denominator. So this is in wave numbers. And so what I do, this is another thing I'd like to give you a tool for. This is what we call an order of magnitude calculation. I don't care about the 3. I don't care about the 8. I really don't care about like a room temperature or a room volume of, 0.02 meters cubed, because Planck's constant is 10 to the minus 34. That's going to really govern, the magnitude of my answer. And the mass is 10 to the minus 26, and the speed of light in centimeters per second is 10 to the 10. So let me just look at the powers of 10. That's what we mean by order of magnitude calculation. You see how handy that is? And it's telling us that the energy level spacing is on the order of 10 to the minus 18 wave numbers. So if that's the delta E between my energy levels, and I have 200 wave numbers of energy at room temperature, then that's what's giving me this 10 to the 30 energy levels are populated, because the energy level spacing is only 10 to the minus 18 wave numbers. So we have tons and tons of energy and lots of molecules in all of the excited states, all the way up to, n equals 10 to the 30. So we say n goes to infinity. Well, this may as well be infinity, right? 10 to the 30 is a huge number, So even if we divided this by 2, we'd go from 6 down to 3 times 10 to the 30. Okay, we multiplied it by 10. Okay, it would be 10 to the 10 to the 31. Okay, so what is it at 100 C? I mean, it's really no big deal, right? Not much different. So here we have an unknown gas, and if this is the partition function at room temperature, why don't I sign it later? Okay. What is it at 100 C? And you say, I can't do this problem because I don't know the particle mass. And this is one of my favorite kinds of problems, because if you take this equation and you see that it's proportional to temperature to the 5/2, then you can go from this proportionality to an equal sign when you do the 2's and 1's, okay? So you could say that partition function is proportional to temperature to the 5/2 power. So if you do ratios, everything else cancels. The pressure is the same, the Planck's constant, Boltzmann's constant, those are the same. Doesn't matter what their power is to the 3/2, because it's the 3/2 on top, 3/2 on bottom, so they're going to all cancel. The mass cancels. Gas constant, number of moles. If those things don't change, then they cancel out. So this is the number one skill in terms of manipulating equations that I like to emphasize, because when I got out of my college career, this was the number one skill I used. No matter how crazy the equation was, if I just wanted to see how it depended upon temperature or what would change if the mass doubled, I could use this kind of technique. Find out how it's proportional, and then do the 1's and 2's. See how similar it is to this number over x equals that number over that number, but you got to take into account the power, the 5/2. And that's probably the number one mistake I see people make on exams. I'll ask them this kind of question, and they'll do, 373 over 273, and they'll have 5 times 10 to the 30 over x, and they'll solve for it, but they didn't take the 5/2 into account. And so then they get totally the wrong answer. So here's the equation. Q2 is equal to 5 times 10 to the 30. And it's, again, 100 C, but we're going to do all of these in Kelvin. Okay, so it's 373 over 298. And to the 5/2 power, that's critical. So it went from 5 times 10 to the 30 up to 8.8 times 10 to the 30. So we populated more energy levels, but not that many more. Okay. Okay. So here's a plot of the translational partition function. And if you need to go back and catch any of this stuff, it's going to be on the video, so you can pick it up. And so you see it goes up. That curve is that temperature to the 5/2 power. It's not quite, it's certainly not linear. It's definitely curved. Okay, but as it goes down to 0 Kelvin, it looks like it approaches 0. But if you were to really zoom in on there, as the quantum effects emerge, what's it going to go to? It's going to go to 1. Okay, so it's going to come in here like that and hit 1, because that would be the ground state. And at the lowest temperature point, the partition function converges to 1, where you just have one energy level with molecules in it. Okay. Does everybody understand what I drew here? That's my little circle. Okay. So let's do another one of those kinds of calculations. If the translational partition function is 5 times 10 to the 30 at room temperature, at what temperature could the translational motion... Oh, wait, did we miss a... No, I think this is the one that has the top hat on. At what temperature could the translational motion be treated as a simple two-level system? So when would we start to see quantum effects emerge? So how cold would we get it for the partition function to equal 2, where you've got population in 2 levels? So we'll have now, one of the Q's is 5 times 10 to the 30, the other Q is 2, and we'll solve for the temperature. Okay, so the same kind of treatment, but here we have now that Q2 is 2, and we'll solve for temperature 2. What temperature would we have? Now, how did we get to this equation, right? We've got temperature to the 5/2 and these partition functions to the first power. So remember your algebra, okay? So if we take this and multiply to the 2/5, both sides, as long as I do something to both sides, we're good. And so over here, the 2's cancel and the 5's cancel, and I have temperature to the first power on the right, and the partition functions to the 2/5 power. That's weird, but it's algebraically fine. Okay, so that's how we flip this equation, so we know the temperature of the partition function dependence in this equation. Would that have tripped you up if you had this problem on the homework? Yeah, we do this a couple of times in this course. When we do adiabatic relationships, we do a lot of this business with the exponents and flipping them over so we can get to the other side of the equation. So now we can solve for the temperature. So we put the 2 on top. Q2 is 2. The Q1 is that 5 times 10 to the 30. We have room temperature for that 5 times 10 to the 30 is 298. And then we solve for T2. Doing that calculation, we end up with 2.1 times 10 to the minus 10 Kelvin. That's really cold, right? So 1/10 of a billionth of a Kelvin. Okay, that's really cold. It's very difficult to achieve. We used to say it was impossible, but with Bose-Einstein condensates, they're starting to see translational quantum effects emerge. It's really crazy. These are ultra cold experiments. They have them in a vacuum. They actually trap the gas molecules with lasers. Isn't that weird? How do you trap something with light? Okay, so write down Bose-Einstein condensate. I'll write it too. Bose. And go to YouTube and look that up. You will love it. Okay. So they trap these molecules in a vacuum system with lasers so that they have the lasers detuned a little bit. So they're not on a transition, like an electronic transition or an infrared transition for the molecule. But if the molecule is coming at that laser, okay, the Doppler effect is that the molecule's moving in this electric field, and so it experiences a higher frequency of that field because it's moving towards it. And that hits the absorption of that atom. And so it absorbs a photon of light, and then it re-emits that photon of light in some other directions. And sometimes that direction is in the direction of the velocity it was going, and it slows down. So the light hits this molecule that's flying into the wind of this molecule, and sometimes it emits it to the right and it goes left, right? Sometimes it emits it behind and it goes faster, but sometimes it emits it in the forward direction and slows down. And this is about translational motion. This is translational motion. So slowing down is cooling. And so they can cool this with lasers and get it all just extremely cold. You know, this is a way to cool something down without having to put it in contact with something that's colder. How do you cool down? You put yourself in contact with something colder. You cool the air, and then you feel cool. It takes that heat away. But trying to get to this cold, if we were trying to get something to 10 to the minus 10 Kelvin, we'd have to put it in contact with something that was that cold. And that kind of defeats the purpose. It's like you have to start that cold before you can make something else that cold. How do we even get anything that cold? And so we have to trap it in a vacuum, totally isolated from this hot environment we're in, and then slow these molecules down to where they really have almost no translational motion. And then we start to see these quantum effects in their translation. Okay. So pretty neat stuff. So let's do a top hat on this one. So this one, I just want to see what you say, okay? When measuring gas pressures or volumes, are you ever going to detect translational quantum effects? Are you? Not is science, but are you? You go out and measure the pressure of your tires in the morning because they look low because it's cold outside. Are you going to detect translational quantum effects? Is anybody still trying, or is it just somebody else? Okay, 18. Okay, good. We got it. All right, I just wanted to see if you had to put it in your own words. Exactly. Negatory. No way. Yeah, you're not going to run into quantum effects of translation. So that's one of the take-home lessons. Manipulating those equations with the proper dependence and exponentials, that's a really big second take-home from today. So most of our storage of energy in gas phase molecules is in translational motion. There's some vibrational excitation, quite a bit of rotation, but this is the big piece. Translational kinetic energy of the gas molecules is where we're storing energy. And we use gases for almost all of our energy applications. We spin turbines, we push pistons. So all of that function is using translational motion. Great. Y'all have a good day. Happy Friday. Yeah.